Let us continue these lectures on algebraic geometry and commutative algebra, and let us recall that we have been last two lectures we have been studying Noetherian modules and Artinian modules, and we have given characterization of Noetherian and Artinian modules and some properties we have given. Now I want to switch to Noetherian rings and Artinian rings. But before that, in the last lecture I have promised that I will give examples of Noetherian models which are not Artinian and Artinian models which are not Noetherian. So, let us start with examples. So, examples. So, one, this I am giving example of a non-Artinian module, Artinian module which is not Noetherian. And in the second we give example of a Noetherian model which is not Artinian. Alright, so my base ring A is the ring of integers. That means we are giving example of an Artinian abelian group which is not Noetherian abelian group. So, in this case abelian groups modules are identical, but anyway let us keep saying Z modules. And now I have this big Z module Q, this is the field of rational numbers, this is a Z module. And in this I am constructing some submodule which is Artinian. So, what is that submodule? I will write that here Z suffix 2, this bracket 2. And what is this? So, you will understand why am I using this notation. It will be clear when I start doing localization. That time this is the notation for something and I want to keep the same notation. So, this is by definition all those fractions A by B such that A, B are integers, B non-zero and B is odd. These are obviously the rational numbers. This means they are rational numbers with denominator not divisible by 2. So, it is obvious that this contains all the integers because I can take in the denominator 1 b equal to 1. So, which is odd. So, this is clear, this is also clear, and it is also clear that this is a subgroup. This is a subgroup of Q plus if you want to be little precise. But this means therefore, this is Z module, Z submodule of Q. Okay. Now, we have a submodule of this Q, therefore, I can consider a quotient module. So, V is Q modulo this Z bracket 2. This is also Z module, and I want to prove that. So, we shall prove that V is Artinian. Let us prove that first. So, what do we have to prove? We have to prove that by earlier equivalences we have to prove that V satisfies DCC, that is V has DCC on submodules. That means any descending chain of submodules of V will become stationary. That is what we want to check. So, for this we just have to study the subgroups of this. This is Z module means subgroup and Z submodule means subgroups. So, what are the subgroups that I want to list of this module? So, the only subgroups of V are two power minus n Z2 mod Z2. We saw in last lecture how to describe the submodules of the quotient module. They are precisely the submodules of the upper module which contain this. They are precisely those submodules. So, look at this, the upper one, this means and n is a natural number. So, I will spell out little bit more about this and then the proof will be more or less obvious. So, what is it? So, if I take 0 submodule here, it is just Z2 cross Z2. If I take half, this is in rational number, and you take the submodule image of this here. That means this, take this, and this contains obviously Z mod Z this bracket 2, because when you multiply this by 2 you become here. So, this is 1, then 1 by 2 square Z2. I have to be clear in the what I am writing, this mod Z2, and increase this, keep increasing the power to natural numbers. So, these are precisely the submodules. Grant this claim for a moment, then what will happen is, so when you take a ascending chain, so first of all this one is contained here, this one is contained in 1 by 4 and so on, this one is contained in 1 by 2 power n Z2 mod Z localize Z2 and so on. And at every stage this is an ascending chain, this will never get terminated, because the this higher power of half will never belong to the earlier one. So, that is easy to check, because this in Z bracket 2 there are no fractions who has a denominator which is even. So, therefore, that cannot happen. So, all this chain is proper chain. This is an ascending chain and it never becomes stationary. So, that first of all shows obviously that this module V and all these are submodules of V. So, they are, so the chain, the ascending chain this of submodules of Z submodules of V is not stationary, and hence V is not Noetherian. So, now we still have to prove two things, that it is not Artinian, it is Artinian, and these are the only subgroups. Alright, once you prove these are the only subgroups, Artinian is easy. So, let me indicate that first. So, if these are the only subgroups, so how do you start the descending chain? At most you can any descending chain of Z submodule starting from V. So, if it does not start from V, you start from V. So, start from V, then you want somebody which is properly contains that, but then the only submodules are half power n times half n Z2. It is this, because these are the only submodules. So, there will exist n in natural numbers. So, there exists n in natural numbers such that this, but the moment you start with n, now you have not much room to decrease, then you can decrease only 1 by 2 power n minus 1. So, this will be 1 by 2 power n minus 1 Z2 mod Z2 and so on. So, ultimately it has to come down to half Z mod 2, not Z mod 2, Z bracket 2, Z bracket 2 and then 0, Z these 2, Z these 2, which is 0 module, 0 submodule of that. So, therefore, V has a DCC. So, this proves V has DCC and hence Artinian. Now, we have to justify that any submodule looks like this. So, if you have any submodule W, if W is a submodule of V, which is remember this is Q mod Z localized at 2, and assume it is non-zero, then what do? You choose, see this W is the submodule of this non-zero means, so that is Z2 is contained in W, we can assume, and this is not proper because this is non-zero, and therefore I can choose. So, therefore, this W should have a fraction whose denominator is odd or whose denominator is even. So, therefore, it has to contain some power of half, and you choose so that it has the least power of. So, choose n least such that 1 by 2 power n belongs to W, and prove that W must be 1/2 power n Z2 this Z2, and this I will leave it for you to check. So, this is check, this is just a little playing with the fractions, numbers and so on. So, we have an example of an Artinian module which is not Noetherian. And second one, now we want to give an example of a Noetherian module, Noetherian module which is not Artinian. So, again the ring is Z and the module V is also Z. So, first of all, note that the descending chain Z contained in Z2, these are even numbers contained in Z2 square, these are integer multiples of 2 square and so on, Z 2 power n contained in Z 2 power n plus 1 and so on. At every stage it is not equal, therefore it is descending properly, which is not stationary. That is, it has no DCC. So, therefore, it is not Artinian. Therefore, Z is not an Artinian Z module. As the course progresses, you will also see how do you prove this much easier way. So, now I want to show that it is Noetherian. That means what? Each ascending chain has becomes a stationary. So, now how do you get an ascending chain? You start with 0, and then you want a submodule of Z, but submodules of Z are precisely the ideals, right. So, then the next will be, and we know all ideals in Z are principal. So, this will be generated by some natural number n. So, it will be Z times n. Now, if I want a bigger one, that means it has to be of the form Z times D, where D divides n, and this is contained here, means n is a multiple of D, that means D divides n. So, further if I want inclusion, then D has to have divisors. So, ultimately there will be a stage where you will reach prime Z P, where P is prime. So, if I want proper chain like that, it can go on till at most the number of divisors of n. It cannot go on for long time, and now we have noted that these ideals are maximal ideals in Z. Therefore, if I want a submodule or ideal which is bigger than this, the only possibility is Z. So, therefore, with the chain will stop here. So, at most it will have number of divisors of this, the non-zero term there, that is the ideal. So, therefore, in any case, therefore, this shows that V equal to Z has DCC, ACC on ideals, which are also same thing as Z submodules. So, therefore, V is Noetherian. Z module. So, in this we have proved, that means in other words we have proved that the ring Z is a Noetherian ring. Recall our definition of a Noetherian ring. A ring is called Noetherian if a ring is called Noetherian if the A module A is Noetherian A module. That is what the definition. Similarly for Artinian ring. Alright, so this proves there is no relation between the Artinian modules and Noetherian modules, but I will prove it soon that Artinian rings are Noetherian, but Noetherian rings need not be Artinian. That you saw in this example, that Z, the ring of integers, is a Noetherian ring, but it is not an Artinian ring because it is not Artinian Z module. Alright, so we will continue. I want to collect now some few statements about the rings and how do you conclude sometimes from the rings the How do you conclude from the modules the ring has some special property. So, in other words, I want to study the category of A modules more to conclude results about the rings. This I will take up later, but right now let us prove a simple lemma which will be useful for alright. The lemma is let as usual A be a ring, commutative always, and V be an A module, then V is Noetherian A module if and only if every A submodule of V is finitely generated. So, this is useful observation because see, remember what we have proved above. We have proved that Z is a Noetherian module or Z. But if you would have used this, it would have been very simple because you know the submodules of Z are precisely the ideals, and ideals are actually principal, therefore finitely generated. So, it would immediately follow from this. So, proof. First, let us prove this way. So, I am assume that V is Noetherian, and I want to prove now that every submodule of V is finitely generated. So, let W be a submodule and A submodule of V, and I want to prove W is finitely generated. Now, consider the subset. See, what is V Noetherian means what? That a arbitrary family of submodules in V have a maximal element with respect to the inclusion. That was the one of the equivalent definitions for the Noetherian modules. So, now consider a subset of submodules of W, that is W prime. W prime is a submodule of W. This is A submodule, and W prime is finitely generated. Of course, this family is obviously non-empty because okay, so I should have said in the beginning we can assume this W is non-zero. So, we can assume this W is non-zero. So, W definitely has non-zero element. I simply take a submodule generated by any element of W. So, if W belongs to W and W is non-zero, I do not even have to, the 0 submodule is here, 0, I do not even have to assume this. So, let us not assume unnecessary things. So, clearly 0 submodule is here, and I do not even need to assume that. So, 0 submodule is always finitely generated. 0 submodule is generated by the empty set or 0 element. So, it is finitely generated and it is there. Therefore, this family of submodules is non-empty, and because of Noetherianness of V, this will have a maximal element. So, let us take that maximal element. So, let W prime be a maximal element in the above family, This exists since V is Noetherian. Now I claim, we prove that claim W prime equal to W, and because it is a maximal element in that family, in by definition W prime is finitely generated, and if I prove W prime equal to W, W will be finitely generated. So, this is obvious, this is by the choice of this W prime, and this W prime is finitely generated, that we know. By definition. Okay. Now, so suppose it is not equal. If W prime is properly contained in W, then consider the submodule A submodule W prime plus a cyclic submodule generated by X with X not in W prime. Because of this, I choose an element X here which is not here, and consider this. This is sum of two submodules. This is smallest submodule which contain both. Now, this one is finitely generated, that is obvious, because it is generated by a generating set of W prime along with X, which is clearly finitely generated. A submodule of W which contain with W prime properly contained in W prime plus AX. But then by definition of that above family, all finitely generated submodules of W belong there. So, this will also belong to that family F. Let us call it F. So, I will go back and this family I am denoting by F. Alright, it belongs to F, but this was the maximal element under inclusion there. So, this contradicts the maximality of W prime in F. Therefore, we proved our claim. So, this proves that W equal to W prime is finitely generated. That is what we wanted to prove. Now, I have to prove the converse. Converse is, if every submodule is finitely generated, then I want to prove V is Noetherian, and that means what? I have to prove that every ascending chain condition on V is stationary. So, start with an ascending chain. So, suppose we are supposing now every A submodule of V is finitely generated, and let start with an ascending chain. So, that I will call it a U naught containing U, containing U1, containing UN, containing this, an ascending chain in S A V inclusion, this ordered set, and U is the union n from 0 or n in n un. This is clearly a submodule of V because of this, because it is a ascending chain. So, U clearly U is an A submodule of V. And hence by assumption, U is of the form finitely generated. So, finitely many elements will generate U. So, that is U is a finite a linear combination of this x1 to xn for some x1 to xn in U. And remember, U was the union, un, n belongs to n, and this is a chain, ascending chain. So, all these guys there exist. So, there exist n large, n in n or u n naught in n, such that, let me call it not n but m here, such that all these x1 to xm they already belong to un naught. They belong to the union. So, they will belong, say let us say x1 x2 belong to one un1 and un2 here, but choose the maximum among them, and then so therefore keep doing this. So, there exists n naught in n such that all of them belong there, but this means, so this means un naught already contains a x1 the submodule generated by x1 to xm, because this is a submodule and it is, these guys are in un naught. This is the smallest submodule which contain that, therefore this, but this is u and u contains un naught because u is a union, therefore equality here. So, therefore u equal to un naught is finitely generated, no is not is finitely generated, but so already up above, after that un equal to un naught for all n bigger equal to n naught, because this was already there, and so that proves, so u V as ACC, that is V is Noetherian. All right. So, now in the, I will stop this, and in the next half I will deduce some consequences from this observation, this lemma. So, we will continue after a short break. Thank you.